Hi everyone. In today's video, we're going to continue our discussions on alkenes and their reactivity. This time, we're going to look at acid-catalyzed hydrations as well as oxymercuration-demercuration reactions. It is my intent that by the end of this video, you will be able to predict the products of acid-catalyzed hydrations, propose arrow push-in mechanisms for the acid-catalyzed hydration reaction, and then you would be able to identify the issue with using acid-catalyzed hydrations in synthesis, and then identify the advantage of using the oxymercuration process to overcome the challenges of the acid-catalyzed hydration. So we'll begin our discussion with the concept of hydration. Hydration is a big family of reactions that involve the addition of water, or formerly the addition of an H and an OH across a double bond. Hydration reactions are readily occurring in the presence of acids. For example, if you have this tri-substituted alkene and you react that with H3O plus, you get this tertiary alcohol as your major product and your secondary alcohols as your minor. Note that H3O plus is essentially just depicting water plus some H plus source. And one possible source of H plus is H2SO4. But really, take any strong acid and dissolve that in water, you're going to get an H3O plus solution. Okay, so let's understand the mechanism of this reaction. You would see a lot of similarities with your hydrohalogenation reactions we've learned in the past. So take your alkene, and this time I'm going to explicitly show all the vinylic hydrogens, and then react your alkene with your H3O plus. In a similar fashion with your hydrohalogenation reaction, the first step is your proton transfer to form a secondary carbocation or a tertiary carbocation. And as we now know, the secondary carbocation is less stable than the tertiary carbocation. And we can probably tell that because we're forming the carbocation in this elementary step, this is going to be rate determining. And so your regioselectivity is introduced in this particular step of the reaction. So both your secondary and your tertiary carbocation are both going to react with water as your nucleophile now in this next step of the reaction. And given that the nucleophile water is attacking a flat carbocation, and the resulting carbon bonded to the oxygen of the water is a chiral center, so therefore two possible stereoisomers are formed. And the ion formed where you have your oxygen with a positive charge on it is called an oxonium ion. So you actually have two possible oxonium ion stereoisomers formed. And now another water molecule can come in and act as a base, deprotonating your product. And what I've shown you here is the proton transfer step that can occur in order to then get your deprotonated products. And here they are. Here are the two minor products of the particular reaction. So now going back to a tertiary carbocation, a water nucleophile can then attack that carbocation, which then gives you your oxonium ion. Water can then come in and deprotonate that oxonium ion. To form your major product. Okay, so here's a few things to note about your acid-catalyzed hydration. Similar to the hydrohalogenation reaction, this reaction is not stereoselective because you're forming these carbocations in which your nucleophile has to attack. So you're dealing with a reaction in which the nucleophile can attack from either side of your carbocation to form two possible products. However, this reaction is indeed regioselective because once again, just like your hydrohalogenation, the major product formed is formed from the most stable carbocation. So when you have multiple carbocations present, the most stable carbocation would lead to the major product. Okay, so let's think about the acid-catalyzed hydration a little bit further. Note that just like your hydrohalogenation reaction, the hydration reaction occurs via the formation of a carbocation. And once you have carbocations, remember that rearrangements can always occur. For example, take this alkene and treat that with H3O plus. You might expect that your major products will be these two products in which your alcohol adds to the more substituted carbon. However, it turns out that these are actually your minor products in your reaction, and your tertiary alcohol is actually your major product in the reaction. And so this is a problem because what if you actually wanted your secondary alcohol from your alkene? You wouldn't be able to just use a simple acid catalyzed hydration to make this synthesis work. We have to go through another means. And the alternate pathway that would help you avoid rearrangements is via the use of a reagent called mercuric acetate. And this is what mercuric acetate looks like. So it's a mercury transition metal that is ligated to two acetate molecules. And here's a short form for mercuric acetate. So we short the acetate to ACO so that we can help save space, but also kind of be more convenient. Mercuric acetate is a salt, and one of those anions can easily dissociate from the salt to form this cationic mercury ion as well as your acetate anion. Importantly, that mercury cation that is formed upon dissociation is a really strong and powerful electrophile and is routinely used in organic chemistry, actually. Okay, so the reaction is called an oxymercuration-demercuration reaction. And that oxymercuration-demercuration reaction actually occurs in two synthetic steps. The first synthetic step is your oxymercuration, and then the second synthetic step is the mercuration. So let's look at the mechanism for the oxymercuration reaction, and then finish up with the workup with the demercuration reaction. So beginning with your alkene and your mercury ion, the alkene can attack the mercury as a nucleophilic attack of an electrophile, which forms this carbocation preferentially. But it turns out that mercury, because it's a transition metal, it does have electrons within the d orbitals. So one pair I'm drawing explicitly with that lone pair on that mercury, and that can actually engage in resonance with your carbocation to form this three-membered ring with your mercury with a formal positive charge. But remember, this is a resonance form, so there's a hybrid molecule you can draw, which puts a partial positive on that secondary carbon as well as a partial positive on the mercury. Okay, so once you get here, though, you can take a nucleophile and really any nucleophile you want in your oxymercuration step. We're going to denote a generic nucleophile with your nuc H, and that nuc H can really be any nucleophile. That nucleophile can then attack the partially formed carbocation and displace the mercury, which once again, because you're attacking a carbon that is resulting into a chiral center, you're going to form two possible stereoisomers. Another nucleophile can come in and engage in a proton transfer step. And this is what you form as a result. So this is the oxymercuration synthetic step. It starts with nucleophilic attack of your mercury ion. You form your mercurinium ion. Following the formation of your mercurinium ion, you engage in a nucleophilic attack on a loss of a leaving group, and then a proton transfer to finish your oxymercuration step. And at this step, you've essentially installed your nucleophile on your substrates. So really all we need to do is get rid of that mercury. And the way we can do this is called the demercuration step, and we use a reducing agent called sodium borohydride. Okay, and the mechanism of this particular synthetic step we're not going to show, but the sodium borohydride is going to essentially lop out that mercury from your carbon chain and replace it with a hydrogen. And you're left with the formal addition of your hydrogen and your nucleophile to in a Markovnikov addition fashion. Okay, so that is your oxymercuration-demercuration reaction mechanism. And remember that is a two synthetic step. Okay, now let's put all of these together to see how the oxymercuration-demercuration reaction is really powerful in synthesis. Okay, so we've seen once again that if you take this alkene and react that with H3O plus, you're going to actually get the rearranged tertiary alcohol as your major product, and your secondary alcohol becomes your minor product. But if you take that same alkene and this time you react that with your mercury acetate in water, and then you do a workup with just sodium borohydride, as we've just talked about in the past, now your water is your nucleophile. The product of this reaction is going to be the formation of your secondary alcohol, and there will be no rearrangement to form that tertiary alcohol. And that's because a carbocation is never fully formed. You actually form your mecurinium ion that does not rearrange. But water is not the only nucleophile that can engage in this type of oxymercuration-demercuration reaction. Change the water to methanol, for example, or pretty much any alcohol. Essentially, what is going to replace is the OH group to an OR group, in this case, an OCH3 group. So the products of this oxymercuration-demercuration is this two stereoisomers of your product. So basically, your two ethers are formed in this particular step. Once again, there's no rearrangement, right? Because we're dealing with the oxymercuration, which involves the formation of that mecurinium ion that does not rearrange because it's not a full carbocation. Now let's look at one more reaction. This time we're reacting that alkene now with your methylamine, CH3NH2. Once again, it's a nucleophile. It has a lone parent nitrogen, and it can spare some protons in your proton transfer step. But you're doing an oxymercuration-demercuration reaction. So once again, you're going to add that nucleophile to the secondary carbon, and there'll be no rearrangement. So the product of that reaction is going to look like this. Okay, so you've got to be able to start seeing some trends, right? So we can replace water with an alcohol or an amine in this oxymercuration-demercuration reaction, and the process is still the same. Okay, so this is really it for your Markovnikov hydration. So if you do the acid-catalyzed hydration, you are going to form a carbocation, and you could potentially go through a rearrangement to form your most stable carbocation. However, if you use the oxymercuration-demercuration reaction, instead of getting any kind of rearrangement, you will not. It would just be a simple Markovnikov addition to the more substituted vinylic carbon. Okay, so it's my hope that you can see that this acid-catalyzed hydration is actually fairly straightforward. If you think about the hydrohalogenation reactions that we've just done, the patterns are basically the same. But we can also identify the issues with any reaction involving a carbocation, which is that there's a possibility of rearrangements that could be terrible for your synthesis. And with the hydration reactions, we can now use a different type of reaction called the oxymercuration-demercuration reaction to do your hydration reaction without any kind of rearrangement. All right. Thank you so much for watching this video, and I will see you in class.